Molality is a unit of a solution's concentration. We can say that we have a 0.5 molal solution or we have a 2.5 molal solution. It tells us a numerical value for the concentration, the amount of solute dissolved in a certain amount of solvent. Now, there's only one particular instance when I can think of molality being used. Molality is involved in what's called colligative properties. Now, a colligative property is going to be a property that depends on the number of particles, not their identity. So it doesn't matter what the substance is. It could be glucose or something else. It could be sucrose. But their identity is not important. It's just how many of them there are. There are 4 situations where you would be asked to use molality in certain, to talk about certain properties of substances. We would be looking at things like vapor pressure, freezing points and boiling points, and osmosis. We probably won't do anything with osmosis. You're going to be looking at that topic in biology. Maybe one problem, but osmosis we're going to leave off for right now. We're going to talk about freezing points and boiling points. I want you to look at the data that I have here that I'm going to put on the board. Let's look at our first experiment, what you should know. Well, I'm going to dissolve some glucose sugar in water. The question is, how will this affect the freezing point? So I'm going to do a graph and show you that if I have pure water, which is concentration in molality would be 0, if there is no solute present, the concentration would be 0 molal. So if I have pure water, you know the normal freezing point. The normal freezing point of pure water is going to be 0 degrees Celsius. So now they do an experiment, and they're going to take a certain amount of water and add enough glucose to make a 1 molal solution. They freeze it and monitor the freezing point. Guess what? The freezing point is not 0. The freezing point goes down. So they add more glucose and dissolve it, freeze that solution, which is now 2 molal. The freezing point goes down. And this continues as they increase the concentration. They look at these points and they think, I think there's a pattern here. I think if you look at this, not a good drawing on my part, that there is a constant slope. So they take their data points and analyze the slope of the line. The slope of the line is going to be called the molal freezing point constant. Kf is equal to the molal freezing point constant. Now, this is going to be a constant value, in this case, for water. But every solvent will have its own particular Kf, molal freezing point constant. Most of the work we do is in aqueous solution. So I would expect you to know this one number. First, look at the line. You can see that it has a negative slope. And when these points were plotted, and the slope of the line, which is a constant, was determined, the molal freezing point constant is accepted to be 1.86 degrees Celsius per mole. In other words, for every 1 mole of concentration, I didn't do that too very well, the freezing point is going to be lowered 1.86 degrees, a constant value. All right, that is one number we need. There is another colligative property, and this colligative property is the boiling point. So, look at this diagram, and you know that pure water has a normal boiling point of 100 degrees Celsius. Now, let's take and increase the concentration to 1, 2, 3. Let's just increase the concentration in a regular interval. So pure water, 0 degrees concentration, boils at 100 degrees Celsius. If you make the solution 1 mole, then the boiling point goes up. 2 mole, 3 mole, 4 mole, and you see the pattern. Here again, the data points seem to indicate a straight line, and a mathematical analysis shows us that these points do fit a straight line, and when you look for the slope here, oops, we have a positive slope, and this slope is going to be called the KB. The KB is a constant. The KB is the mole boiling point constant for water. When the data points were analyzed, a straight line graph was drawn, the slope was calculated. The slope here was found to be positive, and here books are going to vary, so I'm going to put one number up. It's either positive 0.51 or 0.52 degrees Celsius per mole. All right, how are we going to use this mathematically? Well, the freezing point is going to depend on the concentration of our solution. The boiling point is going to depend on the concentration of our solution, but it's related to that concentration by a constant value, the Kf, the Kb. So, let's look at some problems that we can work. And our equations are going to be that the change in the temperature when water freezes is going to be equal to, it's going to be related to the molality, the concentration, times the mole freezing point constant. That's going to be our equation for freezing point changes, and the change in the temperature at which a solution will boil is going to be related through the molality by the Kb, the mole boiling point constant. Let's look at two quick problems. What would the new freezing point be if we had 500 grams of water, 20 grams of a solute, I'm going to explain non-electrolyte later, and the molar mass of the solute was 248 grams per mole? Well, delta TF is going to be equal to the mole freezing point constant. This is a constant value as long as you have water. I know that this value is going to go down, so you can either put a negative here or not. But it's going to change by 1.86 degrees Celsius per mole. And then we need to know the molality. we don't have the molality. So look at what we do have. 20 grams of solute and 0.500 kilograms of water. This is not molality, grams per kilogram. I need it to say moles of solute per kilogram. So I need grams to go away and moles to appear in my numerator by factor labeling. I was given the molar mass of 248 grams is 1 mole. So my units, I've lost my green pen. My units of grams of solute cancel out, leaving me with moles of solute over kilograms of solvent. That is molality. After 2 sig figs, that's going to be 0.16 molal. Check the math. So I would come here and place the molality in to this equation. Molality is going to cross out, and this is going to tell me, by multiplying 1.86 by 16 by 0.16, this is going to tell me the change in the temperature where it freezes. Now remember that for water, the normal freezing point is 0 degrees Celsius. So I'm going to take this value and subtract it from 0, because I'm going to go back to the first board now. It is freezing point depressions. The freezing point is always going to go down. If you have a pure solute, that's going to be the highest freezing point that you will have. As you add more and more solute and make a solution, the freezing point is going to decrease. Just the opposite is true for boiling points. It's going to be boiling point elevation. Let's look at a quick problem. And here at the bottom of the board, what would be the boiling point if 50 grams of glucose were added to 750 grams of water? Well, my equation for this problem is going to be that delta TB is equal to KB times the molality. The KB I'm going to use is 0.51 degrees Celsius per molal. Check and see if your book wants you to use 0.52. And now I have to calculate the molality. I have 50 grams of glucose and 750 grams of water. I'm just going to say 0.750 kilograms of water. That's none of the units I need, so I'm going to have to get rid of grams and go to moles. And for glucose, I know that 180 grams of glucose is 1 mole of glucose. So my grams of glucose cancel out. Moles per kilogram is my molality, and then I multiply that by 0.51. This is going to give me my delta TB, 0.51. Remember, the slope of the line was positive for boiling point changes. The slope of the line for freezing point was a negative number. Freezing points always go down. Freezing point depression. Boiling points always go up. Boiling point elevation. I'm going to be assigning you some problems on Schoology.